anyway. Um,
Screen. Ignacio.
yeah. Now it's working. Yeah.
Okay, perfect. So
So
let's
you
get
can
started.
start when you want.
Great. Hello, everyone, and welcome to the 14th session of the ISRM Young Members Seminar Series. I am Yusuf Golopchi from York University in Canada. Dr. Kimi Suzuki from the University of Chile, Dr. Kiso Kim from Texas A&M University, and I, as part of the ISRM Young Members Group, are happy to co-chair this 14th ISRM Young Members Seminar. It's a great pleasure for us to be here today, and we would like to thank you for attending this 14th session. Before starting, we would like to thank the support received from the International Society of Rock Mechanics and Rock Engineering, and especially to Dr. Sevda Dehkhoda, the ISRM Vice President for Australasia and Chair of the ISRM Young Members Committee. We also would like to thank all the young member representative of national groups who have joined this initiative from Spain, Australia, New Zealand, Japan, China, Chile, and Canada, among others. Finally, we would like to thank Ms. Cecilia Belen-Laskowski Orlandi, Mr. Amir Javaid, and Mr. Nikita Bodarenko for agreeing to present their work in this session. Before our speakers begin, we will take a moment to present key information about the seminar series. This project attempts to promote youth community interested in rock mechanics, including engineers, research scientists, and students, to foster knowledge in rock mechanics among this community, to share experience both in the industry and the academia, to strengthen relation between different countries. We would like to invite a variety of young members to participate in this seminar series. The criteria for the speakers, as shown in the slide, are as follows. You should be an ISRM member, have a maximum age of 35 years old or 40 years if a PhD degree was obtained in the previous 5 years, have worked in rock mechanics and rock engineering for a period no longer than 10 years. Okay, so some information on how to apply for the speaker nomination. The speaker nomination can be made by the nominee's national group or by some other person or organization acquainted with the nominee's work. Self-nomination is also accepted. Nominations are to be addressed to the ISRM Young Members Seminar Series Organizing Committee. On the screen, you can see our contact email. This webinar will be held quarterly, and we invite you all to keep in touch. Okay, great. Now I'll pass the mic to my colleague, Dr. Suzuki, to introduce the first speaker. Kimi, stage is yours.
Thanks, Yusuf. Can you project the presentation, please?
The presentation? Oh, you want me to screen share?
Yes, if you have it with the
sure. Sure. I'll keep. There we go.
Yeah, so now we will present the 3 speakers that we will have today. And for today, each of the presentation will last 20 minutes. And then we will follow with 5 to 10 minutes of questions. So for the smooth running of the seminar, please turn off all the cameras and microphones during the presentation. Please, if you have any question, please use the chat if you are in Zoom or also if you are in YouTube. So first, I will introduce the first speaker, and she's Cecilia Laskorowski, and she's a PhD student at both at the University, National University de la Patagonia San Juan Bosco in Argentina, and she's also at the University Polytechnica de Madrid in Spain. Her PhD thesis is related to the underground storage of CO2, and she's currently part of the Disco to Store project funded by the European Union Eurozone 2020 Research and Innovation Program. Marie Curie. Previous to beginning her postgraduate studies, she participated in research project related to soil stabilization with eco-friendly additives. So she's currently a graduate assistant at the subject elasticity in the civil engineering degree program at the University Nacional de la Patagonia San Juan Bosco in Argentina. So today she will be presenting the talk entitled Partially Depleted Oil and Gas Reservoir Rock as a Possible CO2 Storage, and she will be presenting an experimental study. I will also present the next speaker, and then we will start with the presentation. So if you can go to the next one, Yusuf. So our next speaker, the second one, will be Amir Javaid. He holds a master in engineering geology from the Imperial College London and is currently completing his PhD in civil engineering in the field of rock mechanics at the University of Toronto. Amir's PhD research focused on Bayesian statistical method in characterizing and quantifying the variability and uncertainty exhibited by the in situ stress measurement, and particularly for the design of nuclear waste repositories. His PhD research is being co-sponsored by the Nuclear Waste Management Organization in Toronto, Canada, and also the Swedish Nuclear Waste Management Company in Sweden. Amir has worked as a geotechnical engineer since 2008 on the design of several civil engineering projects involving rock mechanics, and he's also registered as a professional engineer in Ontario, Canada. His presentation will be entitled Characterization of Variability and Uncertainty in situ stress during using Bayesian statistics. And today, our last speaker, if you can go to the next one. Yes, sir. Will be Nikita Bodarenko, and he's a PhD candidate at Civil and Environmental Engineering Department of the University of Illinois Urbana-Champaign, and he's currently part of the Carbon Safe Illinois initiative aimed to accelerate commercial scale use of carbon capture and storage technologies and led by US DOE. Nikita's main research interest is integration of geomechanical and geophysical data across spatial and temporal scales to improve the understanding of complex processes occurring in the subsurface. His presentation will be entitled Geomechanics of Injection Induced Seismicity in Illinois Basin. So that will be our speakers. So let's start with Cecilia.
Well, I think you're hearing me and you're seeing my screen, right?
Yes, all good.
Oh. Well, my name is Cecilia Benelaskowski, and in today's presentation, I will be talking about a little bit about the results obtained this far in the development of my PhD thesis. And the title of the presentation is Partially Depleted Oil and Gas Reservoir Rock as a Possible CO2 Storage, Experimental Study. Okay, as you must know, during the past few years, the global temperature has been rising due to an increase produced in the emission of CO2 to the atmosphere. So if we wanted to mitigate this global warming, we would be right to possible to reduce or at least to maintain constant this increase in the global temperature. So different alternatives have been found, among which storing CO2 in the underground can be found. CO2 can be stored underground, for example, in coal beds, in depleted oil and gas reservoirs, in saline aquifers, and in salt beds. In particular, today I will be speaking about a rock that is found in Argentina in the Gulf of San Jorge Basin that is characterized for being a glauconitic sandstone corresponding to a depleted oil and gas reservoir. So if we wanted to use a certain rock as a CO2 underground storage, we should make a general study in which we should analyze if this is really possible or not. So a series of questions should be made. For example, what changes does this CO2 injection produce in the underground? And if this CO2 injection produces changes, are these changes convenient for CO2 storage? Another question we should be making is what happens with the discontinuities in the reservoir while we are injecting CO2, because the problem with these discontinuities is that they are weak points that could lead to the reservoir's failure while injecting CO2. And lastly, an interesting question to answer will be, could long-term CO2 injection be simulated using parameters obtained from outcrop sample? Okay, I will begin talking about, or my presentation will be centering specifically in what changes the CO2 injection produce in my particular rock chosen. So, in order to answer this question, we considered that it was necessary to study two different types of rocks in laboratory, okay? So we needed to determine the properties of the pristine sandstone because we needed to know with which type of rock we were working, and we had to determine also the characteristics or the properties of CO2-aged specimens. In particular, we were interested in not only comparing the pristine and the carbonated sandstone, but we were also interested in observing what were the changes for different periods of CO2 aging. So, in order to age these pristine specimens, we firstly obtained the specimens from outcrop, and we divided these pristine specimens into two different groups. The first group was the pristine specimens that we left them stored, and afterwards we tested them. And the other group, we aged them into two different aging periods, 30 and 60 days. The aging process basically consisted of introducing these pristine specimens inside a carbonation cell or carbonation chamber, as the one observed in the slide. And in this carbonation cell, the pristine specimens were introduced in a water saturated state. The objective of this was to allow a quicker diffusion of the CO2 inside the porous structure of a rock. Another important clarification that should be made is that the CO2 injected was injected at the supercritical state, because in reality, the CO2 is injected into the underground in a supercritical state. Okay, so once we had our pristine and CO2-aged specimens, we were interested in determining certain properties, mechanical, hydraulic, and also mineralogical properties. From now on, I will briefly mention the results, and in the end, I will be making a general analysis of the whole set of results. Okay, in terms of the determination of the mechanical properties, we did a series, or we performed a series of uniaxial compressive tests, confined compressive tests, tensile tests, and discontinuity shear tests. In the slide, you can observe that, I think you should be able to see my pointer. Okay, that these numbers correspond to the amount of specimens tested, pristine specimen tested, 30-day aged specimens and 60 CO2 aged specimens. Okay, in terms of the determination of the uniaxial compressive strength, we were able to observe in general terms that as the period of aging increased, the compressive strength of this rock decreased. There was a more notorious decrease between the pristine and the 30-day carbonated specimen, but the 60-day carbonated specimen also presented this behavior. Another observation was that the Young's modulus was also reduced, which meant that there seemed to be a change in the behavior of the rock from a fragile behavior to a more ductile one. When we analyzed the triaxial compressive tests performed, we were also able to observe that there was a reduction in the strength of the specimens or of the rock when we aged them. But there was a difference between the behavior of the Young's modulus in this triaxial compressive test and the one presented in the uniaxial compressive tests. In the triaxial compressive test, we could observe that the Young's modulus increased, which meant that instead of becoming more ductile, the behavior became more fragile. The main reason for this is that we believe that the rock, when it is not confined, as it has a lot of discontinuities, the breakage is more fragile. Okay. With these mechanical properties obtained, we were able to obtain a Hoyt-Brown linear regression, and we were able to observe that as the amount of time in which the rock was exposed to CO2 increased, what happened was that there was a reduction in the strength, in the failure strength of the rock. Previously, I also mentioned two things. Firstly, I mentioned that it was interesting to analyze what happened in the discontinuities of our reserve. A discontinuity, for example, could be the one present between the wellbore cement and the rock, the reservoir rock. So in these shear tests, what we did was to test the interface defined between the wellbore cement and the rock. And what we were able to see was that the pristine composite specimens presented a peak shear strength and a residual shear strength, while the CO2 aged samples didn't present this peak. This would be indicating that there is some kind of reaction occurring in the interface that is reducing the shear strength of the interface. And this was presented for all of the confinement pressures at which these tests were performed. Okay, I also mentioned that we determined or we analyzed the evolution of the hydraulic properties of the rock before and after carbonating. We analyzed the permeability using the triaxial cell for soil, and we also analyzed a series of parameters that were related to the porosity by using the mercury intrusion porosimetry. In this slide, we can observe that when comparing the porosity of the pristine sample and the porosity of the carbonated sample, there seems to be a reduction in the porosity. But another interesting aspect to mention is that the mercury intrusion porosimetry basically consists of intruding mercury into the sample and afterwards extruding it. and the remaining mercury indicates the amount of ink bottle type of pores the sample has. And what we can observe is that after carbonating the sample, the amount of mercury that remains inside the sample is less, which means that the amount of ink bottle pores reduces after the carbonation process. Well, on the other hand, we were also able to observe that the pristine sample presented two peaks or two important amount of types of pores. A peak in pores, in small pores that corresponded to the 100 nanometer diameter, and a group of larger pores in this area between 1,000 and 10,000 nanometers. But after carbonating our sample, what we could observe was that the larger pores were notoriously reduced, but the amount of small pores increased also notoriously. Okay. In terms of the permeability, we were able to observe that there was an increase in the permeability of the rock after carbonating it. Lastly, we decided also to perform a series of mineralogical determination of the properties, because we believed that the main reason why the hydraulic and the mechanical properties were changing were due to the reactions produced between the rock and the CO2 being injected. We performed a series of observations in the microscope, analyzing thin layers of the sandstone studied. In this particular presentation, I will only be sharing the results obtained in pristine samples. We were able to observe that the samples presented quartz, which is reasonable as we were working with the sandstone. The sandstone also presented feldspars, carbonatic cement, plagioclase, and glauconitic clasts. That's why I don't remember if I mentioned it, but the sandstone was a glauconitic sandstone. We also performed a series of X-ray diffraction tests in both pristine and carbonated sandstone. What we were able to observe from these X-ray diffraction results was that the plagioclase present in our sandstone were mainly anorthitic and in less amount albitic. We were able to observe that changes were being produced in the plagioclase when the rock was being carbonated. We also performed a series of X-ray fluorescence tests and carbonatic content tests. We were able to observe that there was an increase in the carbonatic content of the sandstone. Okay, so all in all, we could observe that there was a mechanical reduction, a reduction in the mechanical strength, an increase in the Young's modulus, which meant that the rock became more fragile. There was a reduction in the porosity, a reduction in the amount of big pores, but an increase in the small pores, an increase in the permeability, and changes in the mineralogy. Okay, so the changes observed in mineralogy were mainly three. In the first place, we were able to see that there were changes produced, or there were reactions between the CO2 and the plagioclase that produced, on the one hand, clay minerals that migrated and in some way ended in our bigger pores, which ended reducing the amount of big pores we had, also reducing the porosity and increasing the amount of small pores we have. And on the other hand, we were also able to observe that this reaction between the CO2 and the plagioclase produced an increase in the carbonatic content. On the other hand, we were also able to observe that there was a reaction between the glauconite and the CO2. And what I forgot to mention was that in the grain-to-grain contact, there were clay grains. These clay grains also reacted with the CO2 and ended altering also the porosity and the distribution of the pores. This reaction between the clay grains in the grain-to-grain contact also produced a reduction in the mechanical strength and the increase in the Young's modulus. What we believe, I say believe because we haven't yet confirmed it, is that the reason why the permeability is increasing is that during this fines migration and during the carbonation process, the rock is suffering some type of cracking, which would increase the permeability. Among other results, we have begun analyzing are the simulations in COMSOL multiphysics. What we have been analyzing, for example, is a water-saturated porous media in which we are injecting CO2. But we still have to make a lot of work in answering this question. In order to answer this question, that is, could long-term CO2 injection be simulated using parameters obtained from outcrop sample, we would like, for example, to analyze examples like this type, in which we have different reservoir rocks and cap rocks. The idea would be, in this case, to use the outcrop parameters from the rock I have studied. We would be including the discontinuities, for example, the one I have mentioned between the wallboard cement and the reservoir rock. The analysis would be a long-term analysis, and we would like to analyze not only the mechanical behavior, but also the hydraulic and the mineralogical behavior. And that would be all. Thank you very much for your attention and for the invitation to this seminar.
Thanks, Cecilia, for your presentation. So now we will have time, like 5 to 10 minutes for questions. I don't know if someone from Zoom has any question. Maybe you can turn on your microphone or use the chat.
I'd like to have, I have a question. I'd like to ask something, if possible.
Yes, of course.
Well, first of all, congratulations, Cecilia. Very nice, very interesting presentation and vast experimental work carried out, and numerical as well. My question is, well, you showed a graph with some unloading, reloading cycles in a triaxial test. And my question is, did you use them for any calculation or dilation calculations or something like that?
Well, I should mention that the main reason why we did these unloading and reloading cycles were to obtain the post-peak part of the curve. But what we also analyzed, that I wasn't able, of course, of showing it in this presentation, we analyzed on the one hand the variation of the Young's modulus, not only in the unloading and reloading, but also in these areas. And we have also analyzed the latent behavior of the rock during the test.
Okay, thank you. Very beautiful graph, by the way.
Thank you.
Yeah, hi Cecilia, thank you for your presentation. So I have some questions. So I was just wondering, you were showing like these effect. So the first question is, you were mentioning that this is a study for depleted oil and gas reservoirs as a, for the CO2 storage. So what's, in your opinion, the difference between, injecting CO2 into just saline aquifers against, depleted oil and gas reservoirs? So does your rock specimens really represent the depleted oil and gas reservoirs? And, so after the oil and gas reservoirs gets depleted, it will just be filled with, I don't know, like aqueous fluid or so. And then, so rather than just saying, reservoir rocks, what's the purpose, or like your opinions on using the depleted gas and, oil and gas reservoirs?
Well, I think that the main difference is that in the case of the depleted oil and gas reservoirs, they are mainly looked for because they have already contained something, let's say, in some ways similar before. And in the case of the saline aquifers, the problem is that having this saline water, maybe, this brings more problems with the process of injecting the CO2 and all the facilities.
Okay, so you were just referring to like reservoir rocks for your studies to see the effect of CO2. Okay.
Yes, we
okay.
chose a rock that we were able to reach and get samples.
Okay. Yep.
And
okay. Yeah, and then another question is, I was it was quite interesting to see that you were showing that your Young's modulus was increasing while your strength was decreasing, and at the same time for your hydraulic measurements, you were showing that your porosity was decreasing while the permeability was increasing. So, I mean, like, just intuitively thinking, it's actually going against each other for both. So do you have any, like, explanations for those results?
Yes, we are still trying to understand it because, yes, at first, if you say there is less porosity, you would think that the strength would increase. But the thing is that the porosity is decreasing because fines are migrating and they are like decreasing the amount of bigger pores. They are decreasing their diameter, and these fines are not as resistant or don't have the same strength as the rest of the material.
Okay,
and
but
so
but
maybe,
then in
yes,
terms of permeability, shouldn't the permeability also decrease?
that's why we think, and we haven't yet verified it, that maybe there is some type of cracking occurring while we are injecting CO2, and this cracking is increasing the permeability. The thing is that we are not sure yet that the permeability tests we are doing are really representative, because the problem is that we are injecting water and we are not sure that we are not taking, like, we are not dissolving things while we are conducting water through it. So the permeability part is like a little bit
Okay.
down.
All right. Yeah, anyway, thank you for your presentation.
You're welcome.
Yep.
Now we have time for another
presenters
question.
can ask questions as well.
Yes, of course.
I wonder, so you referring to pristine versus 30 days carbonated and 60 days carbonated. So I wonder if you can somehow distinguish between effects of heterogeneity and effect of treatment, because of your if you tested different specimens, they might have just inherent variability of properties. So have you ever tried, let's say, measure permeability on pristine specimen? After that, because permeability measurement is not destructive, after that conduct treatment, and after that measure it once again?
Well, I have to mention two things. On the one hand, you are right with the heterogeneity part, but the thing is that we tried to obtain specimens that we called twin specimens. So, for example, if we took two specimens like this, we had two specimens from our sample, we left this one for pristine analysis, and this one we carbonated it. So we considered that there wasn't heterogeneity because they were basically the same in some way. And on the other hand, the problem with what you're proposing, it would have been ideal, yes. The problem is that the rock is from Argentina, but I am doing my experiment in Spain. So I have the carbonation cell in Argentina. So I am constantly transporting from Argentina to Spain rock. So it's a little bit complicated.
Makes sense. Thank you.
You're welcome.
I think we're on time, but if someone else has any questions. It seems we don't have more questions, but so thanks, Cecilia, very interesting presentation.
Thank you.
So we will continue with Amir, our second presenter today.
Thank you, Dr. Suzuki. Thanks for the introduction you gave about speakers at the beginning. Good afternoon to our audience. We're in the same time zone as we are in, and greetings to whatever the time zones. I understand Cecilia is almost to the bedtime in somewhere in the world. I hope you can all see the screen now.
Yes, now we can see it.
Okay, thanks very much. So let's get into the business of characterization of in situ stress. And in this talk, I'll be taking a perspective that is more applicable to nuclear-based, just to the design of nuclear-based repositories. But it is the approach presented here will be general enough in order to be used to for the design of other underground engineering projects as well. The reason why we are interested in studying stress is that we have enough evidence that there is presence of high in situ stresses in the ground. And that is seen, often observed in excavations in the form of induced stresses, and then the manifestation of those induced stresses. And in some cases, we have these extreme events which are more difficult to deal with, which are the likes of rock bursts. So in situ stress is really a crucial parameter for the design of many underground rock engineering projects. In the context of repository design, we have this familiar concept of repository, which is approximately 500 meters deep below the ground surface. And then we have at this target depth, this network of underground openings. And for those underground openings, what we would want to do is run numerical analysis to evaluate their stability. And for that, we also need to provide input of in situ stresses. And then we can compute the induced stresses around the excavations that are used as part of the safety assessment of these structures. But one problem here is that these applied stresses are often variable in nature, both in magnitudes and orientations. So the question we are trying to get an answer to is that what are the design values that will be representative of the site conditions? Well, first of all, I would want to acknowledge that these slides have been taken by Professor Harrison, who is also attending this webinar. Thanks very much, Professor Harrison, for allowing me to use these slides, because initially these slides were developed by himself. So let's recall ourselves that stress is a tensor, and in its tensorial form, it can be represented in a matrix. Then we can transform these stresses into eigenvalues and their eigenvectors, and the eigenvalues correspond to these principal stresses, principal stress magnitudes, and the eigenvectors correspond to the principal stress orientations. But it is often believed that stress is related to depth. most of the time it is believed that they are related with by a linear function. This is a typical example, the one we have from late 1970s. And what we normally do is we get this estimate of the variability, which is of the model. And this variability, which is part of the model, suggests that stress linearly somehow varies with the depth. And this is often estimated. But there is this randomness or the effect of randomness, which is generally not taken into account. And for these sensitive structures, such as nuclear waste repositories, it is critical to take into account these variability measures. And then we have a fairly recent example where we continue to see these regression. So the question here we raise is this state of the art? Well, clearly it's not, because orientations are ignored in this approach. And stress, as we know, is a tensor. So in our research group, multivariate model has been recently studied, which is truly faithful to the nature of tensorial stress. In terms of the probabilistic model, we believe that the three of these normal stresses, the entities of infinitesimal cube can be represented as a stress matrix, which is in the tensorial form, and the three of these normal stresses will follow their own distributions, and so will be the shear stresses. And in our recent studies, we had been able to come up with an approach which uses multivariate statistics. And in that, we can use only the distinct elements of stress matrix and represent them as a 6-dimensional data vector for the complete 3D stress state. And this way, we have the two parameters of multivariate normal distribution. We have the mean, which is a measure of central position in 6-dimensional space, and then we have a measure of dispersion, which is the variance covariance matrix, and is a 6x6 matrix. One problem with this approach is that how many stress measurements are required for that the designer can confidently use in characterizing in situ stress for the design of nuclear waste repositories. And this is actually this actually led us to think about Bayesian methods and techniques. The problem is this: we have it at some unique sites. For example, this is from SKB Forsmark site in Sweden, and this is a unique case in that it has quite many measurements of the stress. But generally speaking, what we tend to have for most rock engineering projects is this: we would have very limited data, and these are unlikely to provide us converged estimates of statistical parameters such as mean and dispersion. And for this reason, we believe that Bayesian methods of statistics offer a very good alternative solution, where we can combine our understanding of the site, project site, with a limited amount of data, and then can produce reasonably accurate estimates for the site. To introduce the model, as we have seen already, that we believe individual distinct elements of the stress matrix, they follow their own distributions. And then we link these with regression coefficients to the depth below ground surface. And this is the Bayes rule, where we have this posterior to be computed for these regression coefficients. And here we have the prior distribution, which is our prior knowledge of the project site. And this is the data that we have obtained through actual stress measurements at the site. And this is just an integral constant, which tend to normalize our samples for this method. There are some software, specialized software, that are available for free to download. and they are very computationally not very expensive, but very handy to perform these computations. Let's now look at the Forsmark site that is somewhere in Sweden, and on the eastern side of Sweden, we just north of Stockholm, we can see Forsmark site, and that's the location plan for candidate area, which is shown in the red. On the top row, I'll be showing the three normal stress components, and these are the data that's been obtained at this SKB Forsmark site in Sweden using the hollow inclusion overcoring stress measurement technique. And on the bottom, I'll be showing shear stresses. And if these are the solid lines that represents the posterior mean, and they're analogous to what we have seen before, which is normally estimated. That's the mean gradients. And then we have these credible intervals, 95% in this case here, shown with the dashed lines. And this is something unique to Bayesian concept, because in Bayesian statistics, the belief is that the parameters, the statistical parameters of population, they are not known, and we can never actually know them with 100% certainty, and they will be variable themselves. So these results, the one I'm showing on the screen, are based on an uninformative priors. So we are not translating or using or forcing the model to use any of the project site knowledge that we have, but we can actually use informative priors, at least on these two shear components, because we believe that one of the principal stresses has to be subvertical at the project site, as is the case for most flat topographies. Here is the depth of the planned repository at 450 meters, and then these are the distributions that we have obtained using the Markov chain Monte Carlo method, Bayesian computation. And if we were to transform these distributions in principal stresses, which we can, then these are the type of results we see. So on the left-hand side, we see histograms of principal stress magnitudes for these three stresses using the uninformative priors. And on the right-hand side, we have the same results, but using informative priors on sigma 3, which is a function, as we believe, of the weight, overlying weight of the rock. And also, we have used informative priors on tau xy and tau xz, the two vertical shear components, to constrain the orientation, as we will see in the following slides. Then we have these posterior means displayed for these distributions, and we also have these 95% credible intervals. As we can see, if we use informative priors, then the variability and uncertainty of sigma 3 mean stress samples reduces significantly. And if we now look at the orientations using uninformative priors, then that's the case. And this is to remind ourselves that we did talk about this, that our belief at the site is that one of the principal stress component has to be subvertical. And this sort of confirms to that. And if we were to see the informative prior results, they are displayed on the right side. And likewise, we have the posterior means of these vectors displayed, and we have the 95% credible regions here. So what we notice here is that there are certainly improved estimates in that it reduces variability and uncertainty for the case of informative priors. So there is certainly a value in using informative priors if they have the sort of project knowledge available with us, then it's really valuable. And that the designers of repositories, they will have to consider this variability in mean stresses, and this will have to be accounted for these sort of sensitive projects. To summarize, we believe, as we have seen from the results as well, that these Bayesian methods, they hold a promise. They give us reasonably good estimates of the variability of statistical parameters of the population, such as mean and dispersion, and give us a method to quantify the uncertainty probabilistically. And our model is fully faithful to the tensorial nature of stress. And most importantly, that this can be applied to a limited data set, which is often the case for rock engineering projects, for most rock engineering projects, because these tests are expensive. These measurements are difficult to perform, difficult to interpret as well, time consuming, and most importantly, they are expensive. So by using these Bayesian methods, we can incorporate our prior knowledge of the site, which is very valuable side of the Bayesian techniques. And as we have seen for the target depths, we can obtain very reasonable estimates for the design of repositories at the target depth. What we still need to learn is how to identify and define these stress states that are critical to the design. And how would one be able to implement these variable input stresses for the numerical modeling as boundary conditions? And we still need to learn an awful lot of how to use our project knowledge in the form of probability distributions, which is the formal prior in the Bayesian computations, and that we need to have such protocols that these Bayesian techniques can be applied to the design of nuclear-based repositories during different phases of the project. For example, feasibility studies or detailed design construction stage, if observation is to be incorporated later on as well. And with that, I will thank you all. Especially, I'm very grateful to my PhD supervisor, Professor Harrison, who is also attending this talk. I'm also grateful to my co-authors and our sponsors, representative of our sponsors, Dr. Kasani and Dr. Masi Wars, for their support and feedback in this work. I am very grateful to ISRM for giving me this opportunity to present my work here. And I'm grateful to NWMO SKB, those who are sponsoring our research at the University of Toronto. And of course, I'm very grateful to the Civil and Mineral Engineering Department and my colleagues at University of Toronto, together with NSERC, which is National Science and Engineering Research Council here in Canada. And with that, I open the floor to questions. Thank you very much.
Thanks, Samir, for your presentation. Very interesting. Does anyone has any question? Maybe
Yeah, Amir. Oh, sorry.
You can go.
Okay. Thank you. All right, thank you, Amir, for the presentation. Very nice presentation. Very interesting work. So I was wondering, like, this uncertainty of this stress and mean stresses. So in the practical sense, for instance, your application for at the depth of 450 meters, what's like the variance of the mean stress, for instance, that as experimentalists that we should maybe consider practically? So what would be the practical variance of these stresses? And does it matter depending on the depth? And also, like, for these models, how can you do the validation?
Right. To answer this question, I'll be flipping through a few of the slides here. If we go back to this slide here, the one that shows the numerical model. So clearly, the boundary conditions are variable because rock mass beyond the boundary conditions, it comes with also the same defects. For example, fractures, it will be perturbed and so on. So it is logical to assume that the mean stresses applied at the boundaries of these domains will be variable. So that's one part of the question, if I correctly understand.
Okay.
And if I now move on to the results that we have obtained at the target depth.
Mhm.
Here, in terms of the magnitude and both in terms of the orientation. So what we are presenting here on this, displaying on the screen is quite a large sample that's been obtained using, the Monte Carlo simulation or the Markov chain Monte Carlo simulation.
Okay.
But clearly, these cannot be used as an input in the numerical modeling, because numerical modelings are often time consuming. They're very expensive in terms of time, and we cannot perhaps evaluate all these samples. This is one of the area that we are still working on in our research group to identify those critical stress states that should be enough to checked for in the numerical modeling exercises. But yes, of course, we cannot, if it is in thousands, we cannot run 1,000 simulations, practically speaking. So that's an area that we are still working on.
Okay.
But as far as basic techniques are concerned, then we have this hope that if we look at the comparison between uninformative and informative priors,
Mhm.
then we get this reduced variability, which is sort of very optimistic, I'd say, for the designers of these nuclear-based repositories.
Okay. Yeah. All right. Thank you.
Thank you.
I also have a question. Do you
Yeah, I
have
have
a
a
question?
question.
You
Yeah.
can go.
Thank you very much. I mean, it was a great presentation. I have a general question that in here, for example, you have uninformative and informative priors. What are the differences? And as far as I understood, like you realize that the informative priors might have a better information, better result in your Bayesian method. Can you just give a general idea about what are the differences and then how you realize which one works the best?
Right. So if we go back to these data plots here, are these ones here, and I'll go back to this. So you can see in the red box, we believe that in principle, since one of the principal stresses has to be vertical, so the mean gradient has to be an intercept line practically at zero. It should be zero. If one of the principal stresses has to be vertical, then these two vertical shear components, they have to be vertical. But what we're getting from this noisy data, and noise in data is due to many factors. There are temperature considerations, although they're all accounted for, but still there are like model uncertainties, and then the rock mass variability, and all these factors contribute to this huge variability. And stress data is rarely like a neat data set or less variable. Most of the time, we would expect to have these kind of data set for the stress. So in this stress data set, the variability is huge, but the mean we can believe, and I think it's reasonable to believe that mean is somewhere at the zero. And this is shown in our, now I'll go back to the results that we were discussing. This is actually shown with this uninformative analysis as well, that one of the principal stresses is subvertical. So what I have done instead in the informative priors is that used a very tight probability distribution on both tau xy, tau xz and tau yz, the two vertical shear components. So these are very tight distributions, probability distributions, with a mean of 0, and the standard deviation of those is very small for this case. And that allowed us to obtain these better estimates in that there is clearly a significant reduction of variability in all these stress components. I hope this answers your question.
Yeah, makes it clear. Thank you.
Thank you.
I wanted to ask, can you describe the rock mass where you're measuring this? Is this more like heterogeneous, homogeneous? I'm asking because you're showing a lot of variability. But for example, if we check, for example, measurements in mines, you have also other things that are affecting the stresses. So how do you think that this can be applied, for example, for a mine site?
Okay, so first of all, most of us will tend to think that the rock mass at Forsmark site is because since it's a monolithic granite, so they'll tend to think that it's probably not heterogeneous, but I'll differ. It's probably more heterogeneous in the top few 100 meters, where we have more intense fracturing, and that's causing, especially for the stresses, that will cause more perturbation. Now, the dilemma here is that if we go back and have a look at this data again, without any lines on it, then you can clearly notice that we have more stress measurements at the shallower depth, which is more perturbed and more heterogeneous. And we have less stress measurements at the deeper depths, which is considered to be more homogeneous. Yeah, so it's one issue. And sorry, I forgot your second question. One was related to homogeneity and heterogeneity, and what was the second one?
Yeah, because here in Chile, we use a lot of this in mines. So you have also other things that are affecting the stresses. So how do you think if this can be applied with the same success in such cases?
Right. So this is, I believe this is a very important question. This technique presented here today is fairly general, and this can be applied to civil engineering and mining engineering projects. And to give you an example is that if you're dealing with a mining project and nearby, normally what happens is nearby from other projects or other sources, published sources, you will have some information about stress state at the site. And you can certainly collect all those data and then combine them in a form that is suitable as informative priors. And you can use that informative that knowledge in the form of informative priors combined with these limited data. Of course, you will have you're unlikely to get these many stress measurements at a mining project, but you can certainly combine the informative priors or the information that you have from other sources with limited data to give you very reasonable estimates for the design, even in the mining industry.
Mm-hmm. Thanks, Samir. Yeah, I think we are on time for the next presentation.
Yeah, so I'll take over, Kimmy. Thank
Okay.
you. So my name is Kisok Kim. I'm an assistant professor at the Petroleum Engineering Department at Texas A&M University. And it's an honor to introduce you the third speaker, Nikita Bondarenko. He is currently a PhD candidate at the Civil and Environmental Engineering Department of the University of Illinois at Urbana-Champaign. He has been involved in many CO2 storage projects, and where his main research interest is integration of geomechanical and geophysical data across spatial and temporal scales to improve the understanding of complex processes occurring in the subsurface. And today, he will be giving a presentation on the geomechanics of injection-induced seismicity in Illinois Basin. Okay, so Nikita, the stage is yours.
Yeah, thank you very much, Kisok, for introduction me and the ISRM for opportunity to present my research. So, and thank you very much, Amir, for showing us and convincing everyone here that state of stress is three-dimensional and it's very challenging to characterize it. So here we will talk a little bit more about this. But as we know, the subsurface activities are increasing for the different exploration projects and let's say unconventional oil and gas exploration or wastewater disposal. And this activity leads to increasing seismic activity in the regions which were previously aseismic. And this is possess some threat, it's possess some risk for the public perception of these projects, and it needs to be properly addressed. And today we will be focusing on geologic carbon storage applications in Illinois Basin, because here in Illinois Basin we have quite a history of successful projects, and one of them world famous Illinois Basin Decatur project, which was associated with some microseismic activity, which is not strong enough to feel on the surface, but with deep well bore monitoring system, it can be detected. However, the project is located, if we look at the natural seismicity, the project is located in the area where almost no natural seismicity in Illinois happens. So we can be almost sure that all the observed microseismicity is the result of CO2 injection. And during CO2 injection, we observe a lot of clusters of microseismic events with magnitude lower than 1.2, but which was detectable by the seismic network. And in terms of the geologic setup of the IBDP site, the reservoir rock is a saline aquifer, which is named Mount Simon. It was injected in the lower part of Mount Simon sandstone, close to the crystalline basement, which is Precambrian rhyolite in this case. And it should be mentioned that all of the microseismic events, they were located in the crystalline basement. And the third formation, which is of interest for this injection site, is so-called Argenta sandstone, which is intermediate layer between reservoir and crystalline basement. And this formation has significantly lower permeability, so it can partially isolate the crystalline basement from the injection occurring in the reservoir. However, the thickness is changing significantly over the injection site, so it has to be considered in the assessment. There are few mechanisms which can be used to assess the impact of subsurface injection and how it can be associated with induced seismicity. So the most simple and the most straightforward mechanism is just reduction of the effective normal stress acting on weak planes associated with increase of pore pressure. And if we use this, we use more circles to represent this situation, it will be it can be illustrated by shift of the more circle to the left closer to failure envelope. In this case, the microseismicity is usually evenly distributed around the injection well, and if we plot the distance from the injection well to the hypocenters of the microseismicity, it will be the size of this cloud will be growing with time. So if we do this analysis for the Illinois Basin Decatur project, first, we don't have evenly distributed cloud of events. So injection was happening at CCS1 well over here, and we see that there are seismic clusters forming there. Second, we don't observe the diffusion front, so we have a lot of events happening earlier than the pressure reached this location. And finally, if we perform the measurements of the strength of this rocks extracted from this formation, we can see that the injection over pressure to reach failure condition is very high. So it's on the order of 10 MPa, and the maximum over pressure recorded during the project was only 1 MPa. So it seems that the pore pressure change is not the only mechanism to explain this microseismicity, and the next step is to bring and try to understand the coupling between fluid migration and mechanical behavior of the system, because they cannot be considered separately. It's called hydromechanical coupling. And in this case, injection next to the injection well, it will be injection-induced extension. And after that, this extension can change the mechanical state of stress far away from the injection well, even if the pore pressure is not changing in this region. And these effects, they at certain distance, they dominate over the change of the pore pressure, and it has to be considered. And if we again illustrate it on more diagram, in this case, the circle will be changing its size, so it's more complex. And even more than this, in most of the cases of the injection sites, we have different formations involved with different compressibilities, and this different compressibility is one of the reasons behind this heterogeneity in state of stress. So the state of stress next to the contacts of formations with different compressibility will be changing, and we will try to assess it for IBDP site. So depending on the location of the fault or discontinuity of interest, different mechanisms will be playing a role. So we need to have relatively complex assessment tools to predict where the response will be localized. And to build these complex assessment tools, we need to integrate as much data as possible. So we cannot rely on lab testing or only field testing. We need to integrate them together. So we performed intensive laboratory characterization of rock extracted from formations. After that, we used 3D seismic and wellbore data to initialize our numerical domain, and also we will consider the three-dimensional porosity distribution. And the idea is to perform assessment to predict the pre-injection state of stress and how it's changing during the injection, and after that compare it with the observed microseismicity. So first, I will show the highlights of the laboratory characterization. So here we have a lot of types of tests to perform because we want to fully characterize coupled hydromechanical response of tight rock. This rock is permeability is microdarcy to nanodarcy. So it takes very long time and precise calibration of the equipment to characterize the response under isotropic loading at different drainage conditions, so we can measure drained, undrained, and injected response, as well as one-phase and two-phase fluid transport. And of course, because we are talking about rock failure, we need to characterize the strength, which I already showed before, and as well as some more advanced tests I will be talking in the end of my presentation. So in terms of the hydrostatic loading, we measure drained and injected bulk modulus, which represents the compressibility of rock matrix and rock minerals. And we can see for all three formations, so for reservoir rock, for this intermediate, and for basement, both in fractured and intact states. So we can see that the sedimentary rock is significantly more compressible rather than a basement rock, but also presence of fractures, it affects the compressibility, both in case of the rock matrix and in case of the minerals. The second, we performed measurements of fluid transport and some undrained parameters. So in terms of the permeability, as I mentioned, it's in the range. So for the intact crystalline rock, the permeability is somewhere on order of nanodarcy. Most people would say it's impermeable, but we need to understand it to properly assess. Nanodarcy is not infinitely small permeability. And after that, presence of sealed fractures, I'm showing on this image, can increase the permeability of rock by 2 orders of magnitude. But if we load the specimen, after the test, we loaded it axially to open this fracture. So this is how this specimen was made, with open fracture. So in case of the open fracture, it can be as permeable as our reservoir rock. And it's interesting that in terms of the undrained response, the Skempton's B coefficient, the opening of the fracture didn't affect the Skempton's B coefficient significantly. So we can combine these two tests together, the hydrostatic loading and fluid transport properties, to establish porosity permeability relationship, which will show us how change in porosity will will be associated with change in permeability. And we can see that for basement, it's highly sensitive to change of state of stress. So this porosity sensitivity exponent means that even small variations in porosity will be associated with very significant change in permeability. And this is we're getting to the part of on numerical modeling. So we want to assess, to perform this computationally intensive exercise to perform computations on real three-dimensional numerical domain. So in this case, it's we have spatial resolution on the order of 3 to 10 meters, and it's more than 7 million grid points for the whole numerical domain, and we need to resolve relatively complex system of the equations. And at the same time, we also implement here the porosity, three-dimensional porosity estimated from 3D seismic to assess the fluid migration process, as well as some variation in vertical stress due to change of density. And the only way to perform these computations with high spatial resolution domains is most likely using GPU for parallel computations. So we can see that by developing CUDA kernels for the GPU computations, we can make our codes 50 times faster rather than performing computations with CPU, which is very beneficial in terms of the time. So let's say for this domain, it took about 1 day of GPU computations, but if we would use the same code on CPU, it would take more than a few months to perform it. And this is the, I think, very good illustration of the point of the previous speaker, that the state of stress is really three-dimensional. So, of course, we don't show all the components. The model predicts all the components of the stress tensor, but after that, we use stress invariance to calculate the proximity to failure. And proximity to failure, the lower the value, the closer we are to failure. And after that, we can see that the state of stress is really three-dimensional. It's affected by local stratigraphy. And also, in numerical model, we can predict how this proximity to failure is changing during the injection. So we can clearly see the pressure fronts propagating through the reservoir. And at the same time, in the basement, it's only localized in the fault zones where it's higher permeability, but the pressure cannot migrate in intact rock. So this is relatively complex three-dimensional images. The only idea was to show that it's very complex, and now I will show the 2D projections to make it easier to understand. So on this plot, I'm showing the elevation of crystalline basement, so we can definitely see significant variation in stratigraphy of the crystalline basement. So it's more shallow in this area and deeper in these blue areas. And after that, we performed numerical modeling because we know only state of stress at the reservoir interval. So after that, we use this knowledge of state of stress in the reservoir interval and perform numerical modeling to assess the state of stress across the whole domain. And here we can see that it's non-homogeneous, obviously, on a scale of few kilometers. And at the same time, there are zones which are more critically stressed, and it partially correlates with the observed clusters of microseismicity. So they have tendency to be localized in the zones which are more critically stressed before the injection due to local stratigraphy. And at the same time, even how the state of stress is changing during the injection, it also depends on a lot of parameters, including local stratigraphy. So we have to perform these computationally intensive exercises to assess and understand where the microseismic response could be localized. And this just on the previous slide, it was vertical in map view. So these are the two vertical cross sections. So yes, we predict some zones which are more critically stressed, shown with red and warm colors. At the same time, it is not and the clusters of microseismicity, they are shown with white markers. So it's not perfect, but at the same time, we can capture at least some localization. So they have tendency to be localized in more critically stressed zones. And at the same time, it should be noted that to perform computations faster, we used quasi-static approach. So it means we use damping for dynamic. So we don't consider dynamic process directly. So it makes the codes faster, but at the same time, we don't consider this dynamic rupturing directly. And so this is the main limitation if we look at this slide. So we are still relatively far from failure. So we need to change state of stress significantly to initiate failure. And of course, first, as Amir was saying, we have very significant uncertainty of the state of stress, especially it's challenging to measure the major principal stress. So it might be associated, if we underestimated the major principal stress, the whole distribution will be shifted closer to failure. But at the same time, we can try to improve the constitutive behavior because we used Biot poroelasticity to describe the constitutive behavior, while the behavior in this region close to failure, it's not poroelastic. We have failure, meaning that we most likely having some plastic effects and most likely some time-dependent response. So if we, let's say, this is the domain of Biot poroelasticity, low applied differential stress and low exposure time. If we wait long enough, we will have some time-dependent response and creep. If we apply high deviatoric load, we have to consider plastic deformation. But in reality, we have to all of these processes happening simultaneously. So it's we have to consider some viscoelastoplastic behavior, and this is most likely more realistic fault physics models rather than poroelastic one. And to just a highlight of our research in this area, we performed this subcritical stress failure tests where we step by step bringing the material closer to failure, and after that expose it to constant state of stress over prolonged time period to calculate these parameters associated with time dependent response, the shear, the viscosity, shear and bulk viscosity, and just to kind of as an highlight of this research. So this is the more Coulomb framework. So we have a failure envelope, and all the processes, we have instantaneous failure as soon as we reach failure envelope. If a process is happening instantaneously, it means our viscosity is 0. At the same time, below the failure envelope, we have elastic domain, where there is no time-dependent response, or all these processes are infinitely slow. So it means infinite viscosity. So, and as soon as we reach this failure envelope, the material magically switch between these two types of responses. So it's a convenient model, but at the same time, it's not fully representative of the process happening. And by performing this test I mentioned, so we see that this time-dependent response and associated viscosity of the rock, it's significantly changing when we approach the failure envelope. So in this case, it means that we can nucleate the failure, macroscopic failure, even if we are not at the failure envelope, but below that, and expose the material for long time period. We also collected acoustic emission data to try to find some parameters which could help us understand this nucleation process. So this is just, again, as a highlight. So we have the final stage where state of stress is not changing, but at the same time, the acoustic emission activity, the microcracking activity, we can clearly see spikes of the activity, and at the same time the relative distribution of energy of these events is changing. So it's so-called B value in Gutenberg-Richter law, and we can see that prior to, for 1 hour before the macroscopic failure, which happens at this moment, we have a significant variation of B value. And at the same time, if we include some, let's say, pore fluid, it will be even more complex response where we can have quasi-undrained behavior, which will be associated with drop of pore pressure, which has to be considered to understand the process happening in the fault zones. We have to consider these effects. So yes, this is my final slide. So for future projects, it's important to properly combine all the data possible, including the data collected from well borers, from laboratory, and during some numerical assessment to perform comprehensive modeling and at the same time validate the predictions of this model. So the accurate measurements of stress state is very important. It's probably it's the main driving force for the induced seismic response, and characterizing this state of stress is essential to understand the localization of this response. And most likely we need to go beyond just pore elastic models to predict all the complexity of the process. So thank you very much for the opportunity to present. And if you have any questions or suggestions and ideas, I will be happy to address them.
Okay, thank you very much, Nikita, for your great presentation. It was very interesting work. And any questions from the audience?
Yes, if I can go first.
Yes.
Yes, please.
Thank you. Thank you, Nikita. Thanks very much for the very interesting presentation and on a very interesting topic. I wonder if you have considered using any non-linear strength criterion instead of using a linear criterion. You've shown us that you consider the linear strength criterion, but I wonder if you have
Just give
considered
me a
the
second.
non-linear strength criterion.
Sorry. Yes, so this is
Yeah,
our
yeah.
experimental data. So definitely, so if we want to consider some non-linearities just in the area of low stresses. So yes, well, at the same time, it's challenging to characterize this material just because it has pre-existing fractures. We have very limited number of cores extracted from depth of 2 kilometers. So here, let's say for the crystalline basement, we performed 3 tests. So this is the uniaxial compression test. So we had to perform to estimate strength in this area, we would have to perform triaxial extension or uniaxial extension tests, which is challenging to perform. So in general, most likely it will be, but at the same time, we already shifted the failure envelope to zero cohesion. So it's I think we on the lower boundary for the strength because we already consider zero cohesion. But at the same time, yes, most likely it will be slightly more beneficial in terms of the absolute values for the this proximity to failure. At the same time, it just will be kind of in terms of the structure of this distribution of the state of stress, it would remain the same.
Thanks very much. I had this question in my mind because if we look at Argenta data, the one you're showing in red, and for that rock unit, especially if we look at the last one, which is closer to an effective normal stress of 80 megapascals. So do you think it's an indication of some non-linearity in the response, or do you think it could be related to variability of a linear envelope?
I would say because we are still working on very limited. So you see, for the Precambrian rhyolite, we had only 3 data points at all because it was when we tried to prepare the specimen, they were just failing along some pre-existing planes. For Argenta, we were more successful. So it might be some variability in terms of the heterogeneity of the specimens, but at the same time, this high level of stress, because this again, it's slightly changing, but in Argenta it's relatively close to the state of stress in the reservoir, so we don't expect to reach failure somewhere here. So most likely it's in this area. But yeah, I would say performing some characterization of nonlinear strength would be important for the properly addressing it like more accurately. But at the same time, we have to, let's say, heterogeneity of, because for numerical model, we just included heterogeneous porosity. The heterogeneous elastic properties would be, they are also heterogeneous. So somewhere we have more compliant material, somewhere we have stiffer material. So it is kind of limitations how much we can include inside and how much we know about the subsurface. And we have to do better there. But thank you.
Okay, thanks very much. Thank you.
Okay,
Okay.
if I can go.
Yes, sure.
Okay, thanks, Kismo. Oh, okay, very interesting topic and great presentation, Nikita. I have two questions. In terms of experimental tests, the first one is for the experimental test that you mentioned that you were using some different types of experimental tests, like time dependence. Like I was wondering, how long did you let each creep took place? Because I remember at some point you were saying you increase it until it get to the breakage. Okay, so did you let the primary creep, secondary creep? I think you will let, because for going to the tertiary creep, it will take a lot of time. So my first question is in terms of experimental tests, that how long your each test took place, how long it took place. And the second one is for the numerical model, that what software they
Can I
use
first
and how
answer?
did you?
Okay.
Okay, sure. Go
Because
on,
it will
please.
be, I will forget the second one and you will have to repeat.
Okay.
So
Sure.
in terms of the experimental time, it's usually on order of few days, just because we step by step bringing it closer and closer to the failure envelope. So here it's a real example of one of the tests, and this is so it's not illustration. It's so we have. So this is associated. This part is associated with change of the stress, and after that we have some few, probably 5 to 10 minutes of this primary creep, which is decelerating, and after that it's more or less steady state. We have longer stages where we convert that it's linear accumulation of strain. But in terms why we finish it within 1 day is just because we are getting closer and closer to failure envelope, and you can see that the final moment where we start to have tertiary. So over here, the stage 1, it's a tertiary stage. It's just because we are almost at the failure envelope. And in this case, you can see that all this time-dependent response. So if we are here, it will take 100 days to accumulate to nucleate this macroscopic failure. When we are over here, the viscosity is changing almost by 2 orders of magnitude. So instead of 100 days, it will be 1 day. Again, it's just some numbers from nowhere. So in reality, if we very close on failure envelope, it's just a matter of hours most likely. So.
And how did you choose the load? What is it? Is it some percentage of UCF?
Yes, so we more or less know the failure envelope of this material. Of course, it is there are some uncertainties there, but we know what to expect in terms of the strength, instantaneous strength when we just loading until failure. And after that, we usually start at somewhere 50 to 55% of the maximum expected, and after that, by small steps, we are just bringing it closer and closer to failure. So it's kind of the most safest option is to start far away from failure, and after that, step by step. And acoustic emission is very useful in this case because it's difficult to see the nucleation in terms of the deformation. The activity of microcracking is significantly more sensitive to that. I have probably some illustration for that, but it will take me a few seconds to find it. Yes. So let's say over here, we can see that even 3 stages before, so this is secondary stage, but it starts growing the activity. So we can see the increase in the activity and associated B values there, but kind of we still need to do better characterization of acoustic emission. And the second question, I got the idea what you were asking in terms of the software. It's because with these GPU calculations, it's very important how the memory access is managed. So if we don't read or write data in memory, because the whole data set, which has to be kind of modified in one iteration of numerical code, because it's 7 million grid points. So it's more than 7 million grid points. After that, all 6 components of stress tensor and things like this. So it's a lot of the. So it's like on order of few gigabytes on each iteration. We need to modify them. So if we do it inappropriately, so we read the data and don't use it, it will not give you this performance increase. It will be 2 times faster, 3 times faster. So for that purpose, we had to develop our own code. So we use finite difference method, the most simple explicit finite difference. And after that, write first code in MATLAB for the CPU computations. And after that, using when we kind of benchmark our code in MATLAB, we translate it to CUDA-C to perform the computation. So it's in-house codes. Well, if you're interested, we have we just submitted the paper for GHR where the codes for this particular case are uploaded. So if you're interested, it's and there is a preprint available, so it is downloadable even now.
So, and how did you use it? Thank you very much. It makes it quite clear. So you were using GPU instead of CPU to accelerate your simulation, and I just wanted to know, how did you validate your numerical models? Was it based on what you were doing with the experimental test, and how was the whole validation of your numerical model? If you can enlighten me about that.
Let me check if I have a good slide over here somewhere in the back of my presentation. So I might not have. So first with
the general idea.
Yeah, so we first benchmarked our models versus some existing analytical solutions. So we step by step, first we kind of developed the code for diffusion, so which just model diffusion process uncoupled. And after that, validated versus error functions and things like this, the analytical solutions. After that, we developed the code for elasticity and benchmark it versus elasticity. And step by step, we are bringing it to more more and more complex pieces in the code. So again, I don't know, it sounds like promoting of some of our recent presentations, but also there is it will be on ARMA this in a week. We exactly put there the article on how to develop step by step and validate it. So it might be of interest to see there. So it's but we validated first versus analytical solutions, and after that used it as input our laboratory data to collaborate the response.
Okay, great. Thank you very much. Thank you for your
question.
Yeah, Nikita, I also let me just ask you one last question. So for the simulation, you are you're not doing multi-phase flow, right? It's just pore pressure.
Yes.
Single phase flow. Okay.
Yes.
And so my question is, like, I mean, you haven't done it yet, but so there's this, arguments or, discussions on the pressure plume because of this interest in this whole, CO2 storage, monitoring and verification, validation, everything. So they're very much interested in the CO2 plume migration versus the pressure plume migration. So from your experience and your research, like, do you expect like some of a big difference between those two, or could you even see those in your simulations?
Yes. So, well, it's kind of part of validation. It will address part of the question. So we had some preliminary studies in terms of the multi-phase flow. So it's uncoupled, but in terms of the size of the plume and size of overpressure. So if you look on this animation on the right, so this is the saturation. So it's like when it's one, it means it's your plume, and at the same time, this is the pore pressure, and you can see that kind of plume is associated with significant change of so overpressure is further away rather than saturation. So plume is smaller than the zone of disturbance. So it's just an illustration, so it's not very precise, but it gives you an understanding. But the second thing which is very important to consider is let's say as I said, the heterogeneous, because most of this assessment they performed on relatively simple numerical domains. So it's a layered cake structure where all the formations are kind of flat, and at the same time all the properties are homogeneous. Here we made the first step, we put heterogeneous porosity, and after that used the porosity permeability to estimate what is the heterogeneous permeability. And so this is the permeability, and you can see because the porosity is changing, permeability is changing, and we use our lab data to calibrate it. So the overpressure and like fluid flow is localized in the zones which are more porous. In this case, so it's I would be careful in terms of using very simplified numerical domains to predict the structure of the plume, because it will be affecting the size of the plume, so it will be localized and still localized in these high porosity zones. And this is kind of relatively usual for the formations because they are heterogeneous, there are different geologic histories. So it is, well, unfortunately, I don't have a good answer. The only way I can what I can suggest is we have to develop complex models, unfortunately. We cannot rely on most likely just on machine learning to predict everything, just because the problem is complex. We need some complex solutions for that. But thank you for your question.
Yeah, all right. Yep. Thank you very much, Nikita. So let me share my screen.
Stop sharing. Yes.
So yes, so thank you everyone for attending the seminar today. Stay tuned on the next seminars and also other ISRM young members activities that we are planning to do. And then we have our webpage and also Twitter account and then LinkedIn page. So if you're interested, please take a look into what we are doing. And then also you can still see my screen, right? Yes. Okay, and then with that, we would like to finish our presentation. Please contact us to if you would like to participate, suggest any speakers, or suggest yourself to participate in the following seminars. You're welcome to contact us. And special thanks, of course, to the ISRM and also from the supports from the vice presidents from the Latin America, Europe, Africa, Esteban, Muriel, and Yanni. And with that, we would like to finish our seminar. So thank you, everyone, and we'll see you at the next seminar.
Thanks, everyone.
Okay, thank you.
Bye. Thanks.
Thank you.